Yeah, thank you very much. Again, for my introduction, my name is Szabo, and I'm a postdoc at the Space Sciences Laboratory of the University of California in Berkeley. And I'm giving a update on our research on the direct ion precipitation of the lunar polar regions. Now, ions that impact the north and the south pole of the moon's surface contribute to a various number of different effects. And in particular, the implantation of volatile elements is important. And protons can also contribute in different forms to the formation of water and ice there. But on the other hand, you also expect erosive effects, such as the sputtering, especially of ices, that can be or is assumed to be a non-negligible contribution to the destruction of ices in the polar regions. Now, in recent years, there has been some research on studying the different ion fluxes that precipitate the polar regions. I show an example here of a work by Rhodes and Farrell that showed how a solar wind plasma can be deflected into a crater near the pole region that would otherwise be non-accessible. Similarly, there have been reported from Artemis measurements that especially when the moon is in the Earth's magnetotail, that there is a population of non-ecliptic ions that has the right impact angles to access such polar craters. Now, the Artemis mission overall has given us several important insights over its many years of operation. But there are some drawbacks for studying the polar regions because, as you can see in this animation here, both Artemis probes operate on an almost ecliptic orbit, and its ion measurements don't allow any or don't give any direct mass information. And in order to extend the previous findings of the Artemis mission, we have now looked at data from the Kaguya mission that was operated by the Japanese Space Agency between 2007 and 2009. And for our case here, it has the advantage that it was operating on a polar orbit at a very low altitude, mostly around 100 kilometers. And one of its two ion instruments allows the mass resolution by recording the time of flight of ions. And we want to use the data of the Kaguya mission to answer mostly two questions. In particular, what are different or what are other contributions, such as reflected ions that might gyrate into the polar regions, that will contribute to both implantation as well as erosion in the poles. On the other hand, we want to look at which ion species actually precipitate the poles, because it will be very different if you have a proton or, for example, an oxygen ions, as heavier ions will also contribute much more to sputtering. Now, to give you an example of how such Kaguya measurements look like, I have a sketch here on the side showing the two instruments. The one IEA in yellow only records the energy of the ions and is always pointed away from the moon. And you can see the corresponding data for a single measurement day here, or for a few hours. And the second instrument, IMA in blue, is always pointed towards the moon. And this IMA instrument has the mass information. And while the moon takes up a large part of the field of view, it's not only measuring the ions coming from the lunar surface. As you can see here in this first example, corresponding to the position over the North Pole, you can see the gray bar here. We can actually measure the solar wind in both IEA and IMA. And over the subsolar point, IMA then measures reflected and sputtered ions, while over the South Pole, you again see the solar wind in both instruments, while at the night side, either instrument does not have many counts there. So looking first at the data from the IEA measurements, again, this is the one pointing away from the lunar surface. This allowed us very nicely to collect the data over the whole mission time and project ion measurements onto the surface of the moon. And you can see a compilation of these measurements here on the left, where the ion flux is plotted over latitude and longitude on the surface in SSE coordinates. So you see, as you would expect, the most flux at the subsolar point. And we compared this to Artemis measurements, where we see the flux over energy. The Kaguya results over the subsolar point are quite similar, with some small offsets, but you have to keep in mind there was a different operation time, and some slight calibration differences can also be expected here. Now over this North Pole, shown here in blue, and over the South Pole, we see significantly lower ion fluxes. There is a small north-south discrepancy visible here. This is most likely due to statistical issues, but we'll have to take a bit more look into that. But compared to the Artemis measurements, again, the fluxes here are similar, especially in comparison to the subsolar flux. Sorry. But in order to compare the Kaguya measurements to the Artemis data, we only looked at impact angles smaller than 45 degrees in reference to the local surface normal. Now, if we increase this to 90 degrees, so take into account all of the ion counts, we see that the fluxes between several 100 and several EV and several keV significantly go up. Now, this is, of course, in part due to the solar wind hitting at very oblique incidence angles. But these Kaguya measurements now help us to really quantify how large of a flux precipitates the polar regions. And it shows here it is increased compared to the previous Artemis observations, but still 2 to 3 orders magnitude lower than what you have at the subsolar point. For the second instrument, IMA, we wanted to look at the composition of precipitating ions, and this is especially interesting in the tail region because the composition there is much less constrained than you would expect it from the solar wind. And for this reason, we compiled all of the IMA time of flight measurements when the mission was in the Earth's tail region. And you can see such a compilation here with counts plotted over the ion energy on the y-axis and the time of flight on the x-axis, with lower time of flight corresponding to lighter ions. So logically, this large peak here can be attributed mostly to protons, but due to the instrument design, we have a small overlap with helium there. But we also see several peaks of heavier ions. In particular, we can identify 2 oxygen peaks. The 2 peaks are again due to the instrument design. We also have carbon, sodium, as well as heavier peaks such as potassium, aluminium, or argon. And a large part of those peaks will definitely come from the lunar surface. And this is very much an ongoing research that we have to filter now, these signals, to really see what are the ions that originate from the moon and what are the ions that come from space and are actually able to precipitate the polar regions. And this is more filtering that needs to be done, but we definitely have enough signal from the Kaguya mission to nicely identify different contributions.
Just a 2-minute warning there. Yep.
Yeah, to summarize my findings, or our findings, we have used the data from the Kaguya mission to study the ion fluxes that impact the polar regions. And we see from the IEA measurements, where we get fluxes over energy, that we see significant fluxes at energies of several 100 to a keV, but again, much lower than the subsolar point. And the mass resolution of Kaguya allows us to identify several different elements very nicely. There is enough signal available, and it is now very much an ongoing work still to identify which of these elements actually impact the north and south pole of the lunar surface. Thank you very much, and I'm happy to answer any questions.
Great. So, Paul, there's nothing in the chat right now. So I'll let you take kind of the first question in the room, and then we can come back to the chat.
Yeah, Tom Orlando at Georgia Tech. So I'm interested in the ions that you see that may be coming from the moon. Mm-hmm. And the question I have is, so the ions that are incident can sputter, but there's also electron fluxes to the surface that are known to remove ions. And so I'm wondering if you have any information on the electron fluxes as well.
I mean, Kaguya did record electron fluxes. Basically, it was a similar design. Each of these ion instruments had an electron instrument attached to it as well. So we could look at the data here. Personally, I've not yet looked in that detail that I can give you much input.
It'd be pretty interesting to look at, because the cross sections for ion removal for electrons will be a bit higher than the proton bombardment.
Yeah, that's a very interesting point. Thank you.
Okay, Paul, back to the chat. I guess just the question that I had is, would you expect the composition of the incoming ions to be different at the subsolar point than versus the poles? Like you're identifying heavier ions, but do you think that there'd be a larger or lower proportion of heavier ions at the subsolar point versus the poles?
It depends a bit on which source we're looking at. If we're looking at specifically, let's say oxygen ions that have been reported in, you know, sometimes called the Earth wind, but basically from the Earth's magnetosphere, then no. But if you have ions that are originally maybe sputtered from the lunar surface, but then due to the direction of electromagnetic fields, especially the induced electric field, might get accelerated towards the lunar surface, then I could imagine a difference. But then again, there is the question if we can actually observe them at an altitude of 100 kilometers, that might be a limiting factor there.
Yeah, sure.